Hi students, in this clip we will discuss about toroid as we have discussed about solenoid in the previous clip. Toroid is also one type of a solenoid, but it contains number of turns above the conductor. So you can just say that it is called as a large number of uh, insulated material, and it's a number of tons. Basically it is conductor, but we have just coated it for it is metallic wire but coated with the insulator, so they both are nullifying effect of each other. In a normal word you can say that toroid is called as endless solenoid. So you have just learned that solenoid is like a spiral shape. So toroid is also of like the same, but it is placed on the conductor. So on the conductor, I have just mounted such type of arrangement. So for better understanding, I have made such type of arrangement for you. Let's say this is the white wire. Actually, it is conductor metal, and on that I have just wounded so many wires. If you practically see such type of toroid, these wires are not making such type of distances between them. They are very much closely attached. So when I have just connected such two type of both the paths, so you can see that there are two different paths I have. One is the first one. You can see that one is the first one where I can find it out. Very first wire current is going inside and current is coming outside, and this is the conductor. On that I have placed such type of wires which are also made up of a metal. So such type of arrangement is look like a toroid. I have just opened it. So in a next, as gradually we are moving forward to the theorem part, we will discuss about its actual geometry. So you can see that in the figure I have mentioned that different points. Let's say this is the center of my toroid O, and that is one point P, that is one point S, and another point which is beyond the toroid, that is called as a Q. So you can say that ideally only point S is in contact with the toroid or on the toroid, and point Q and point P are not on the toroid where your center is O. So let's say again we are focusing on this toroid. So you can just see that over here this is your actual toroid. The point which I have mentioned is called as a center, which is over here in the hollow part, and point P which I am talking about, this point P is somewhere in between but not on the toroid. So you can see that. So this is the primary arrangement. I have one point that is called as S. So you can see that point S is on this point over here on toroid, and I have mentioned that point Q. So point Q is somewhere over here outside, somewhere over here outside, but not on the toroid. So you can see that my practical arrangement of the toroid, if you just focus this one, you can see that. So this is the hollow part. This hollow part contains that 2 points, point P and O, where O is at the center and P is somewhere in between, where S is on the surface and Q is somewhere out from my point P. So you can see that current is only passing through such type of points. So again I am just showing you a figure. You have again a toroid. I have just cut it for you, and you can just see that it's a internal part, and that point P, internal part and point P, its radius is called as R1 part. Then on point S I have my radius is called as R2 part, and then at outside which is at R3 part. So you can see that only current is passing from this much loop, which is only part of S, which is at only R2 radiuses. So after understanding of this figure, we can just use two type of points, either inside or either outside or on surface. So let's say I'm talking about point P. You can see that point P is inside but there is no current. So integration B dot dl is equals to mu 0 I, but you are aware that my current will be 0. So even though I am just opening this part BDL cos 0, it will make a current 0. So for this one part, my magnetic field at the center will be 0. uh, Next point, that is called as a second point. Let's say I'm just talking about point Q, which is outside and which is actually at a radius r3. So this point is at outside point Q. So integration again b dot dl is equals to mu 0 I. So I can have again b3 will be again 0. But I want to discuss about that point, third one, that is called as on point S, which is already where current is passing. So these are the points where magnetic field is coming outside, and these are the cross points where you can see that my magnetic field lines are going inside. So these are the points of a dot and cross. So point S we are talking about. So point S contains integration of b dot dl. Here my current is actually passing because point S is on the toroid. So first of all I am just integrating b. Integration of dl is called as a 2 pi r2, and angle is called as a cos 0 mu 0 into I. So you can just say that my equation will be b 2 pi r2 mu 0 I. So now I am just putting these values and simplifying it for you. So b equals to mu 0 I divided by 2 pi r2. For n such type of loops, I have just talking about only one loop, so I can have small n equals to n divided by 2 pi r2. In solenoid also we have discussed about this thing, number of turns or number of loops per length or radius. So my equation will be b is equals to mu 0 ni. This is the same equation which we have learnt in solenoid. So there is no difference between the solenoid and toroid in equation point of view, but its a practical arrangement is something different. As you can see, it is called as an endless number of turns, and that was only bounded on the current carrying loop, while my solenoid is only merely a loops or turns. This is the primary difference we have. Now there is a question toggling in your mind that what is the primary difference between that current carrying loop or solenoid and toroid. So for you I am just simplifying it. So first of all we can just say that similarities between solenoid and toroid. So first of all we will discuss about similarities. First of all you can just say that both are electromagnets. Number 2, it is containing electric current. Then and then we can get its magnetic field. Third part is called as a both contains the same formula, which is called as a b is equals to mu 0 ni or mu ni. So this is the primary relationship between the our solenoid and toroid. Now differences. First difference between the solenoid and toroid. That is called as it is containing cylindrical type of shape, while the my toroid contains circular because it is somehow called as a Duff ring. Second point, which is containing difference between, that is called as our magnetic field is decreasing outside and it is stronger inside. You can say here magnetic field is inside, but because of the equal amount of number of turns it will be 0. Third one is called as it's containing a, a, uniform magnetic field. and here you can say that is called as a non-uniform magnetic field. So these are the primitive differences and similarities between our uh, solenoid and toroid. So you are right now quite familiar with the differences and similarities of a solenoid and toroid. You can also accumulate different type of similarities and dissimilarities as per your convenience, understanding and equation point of view, but I have only highlighted a few for you, so you are quite familiar with the solenoid and toroid geometry. Thank you. Hello students, at the junction of this chapter we have learned that so many formulas, so many relationship differences and similarities between solenoid, toroid and whatnot. Right now we are at the junction of this point where we will discuss about or capable enough to discuss or bring it out differences and similarities between electric and magnetic field. So first of all we will just discuss about so many similarities, and then we will discuss about its differences. So students, we have learned that so many similarities. So first of all I am just comparing this part. Let's say both our electric and magnetic forces are or fields of long range, because they are existing at a very long distances. As you can just say that E is having relationship, it is called as inversely proportional. So E is inversely proportional to 1 upon r square, and r is larger, E is smaller. Same is the course for the B, which is proportional to r square. Though you are aware that whenever you have a electric dipole moment, you have over here that is called as a P, which is called as a electric dipole moment, while in the B we have a magnetic dipole moment. Generally we are just calling it as a M. So whenever such type of relationships are there, this relationship is supposed to be changed. It is not 1 upon r square, it is called as a 1 upon r cube. So this is very primitive differences first of all we have. Next one is called as a this both E, both our electric field and magnetic field follows or possess superposition theorem. So you can just say that there would be a sum of so many electric fields that is starting from E1 E2 up to so on, and that is called as up to n. And so is the course for magnetic field, it is starting from B1 B2 up to so on, and that is called as a Bn. So such type of primary differences similarities we have. Next one is that our electric field is only because of that electric charge q, while magnetic field is only available from our current carrying conductor or current segment. So you I am just using this word, that is only because of current segment. So you can just say that these are the rules, these are the similarities of our electric field and magnetic field lines. Now we are discussing about dissimilarities or differences. Very first difference is that our electric charge, which is called as a scalar quantity, while my magnetic, or you can say current segment, which is I have mentioned in throughout my all lectures, that is called as a vector quantity. Next is called as our electric part, which is following dot product, and when my magnetic is following that cross product. Last not least is also important one, electric field is independent of angle theta, while my magnetic field is dependent on angle theta. So in electric field we are not bothering about dot or cross notation, because we are habitual that electric field lines are passing from plus to minus, which is vice versa for the dipole. But in magnetic field we have to be very cautious about our thumb rule, where our magnetic field lines are entering, where it is going outside. So I have just pointed it out, similarities and differences for you. So be careful in this chapter. Either in a school or board exams they are asking for the 2 or 3 marks, 2 marks theory basically, either the similarity and differences of a solenoid and toroid, or they may ask you that what are the similarities of electric field and magnetic field. Yes, you can also point it out that there is one more similarity, that you have integration, that E dot dl is called as sigma q by epsilon 0. In same course you have here ampere circuital rule, instead of dl you have da, b dot dl, that is called as a mu 0, and these are the similarities. But also you can also point it out so many differences as well. So keep in mind these formulas, keep in mind this relationship, because as usually I am using such type of words in regular lectures, that whenever you have thoroughly studied chapter number 1 and 2 static electricity, you will be capable enough to find it out, similarities, differences and relationship of magnetic field as well, because both the chapters have some of the differences of a concept, some of the constants. Otherwise both chapter deals with the such type of some of the primitive common factor or characteristics. So keep in mind and focus on such type of similarities and differences in, and accumulate both those similarities and differences in your mind. Thank you.